In this work, we introduced DRaM-LHM, an iterative 6-stove camera pose estimation method built on the new algebraic framework, which we call the adjugate Quaternion. To set the stage, we first review the perspective endpoint or PNP problem. PNP estimates a camera's absolute pose from known 3D points in their 2D image projections, giving calibrated intrinsics by minimizing a projective geometry objective. The PNP problem can be solved either analytically or iteratively by minimizing one of three standard objectives: reprojection error, Z-prime error, or collinearity error, as illustrated on the left. Our approach leverages an advanced algebraic framework for initialization and then iteratively minimizes the collinearity error. Next, we introduce the algebraic framework at the core of our method, the adjugate Quaternion, originally developed by Dr. Andrew Hansen. Adjugate variables are quadratic terms of the unit Quaternion, defining a quadratic mapping from R10 to the S3 manifold. Like the unit Quaternion, they require constraints to remain on the 3 sphere, but in this case, a total of 7 additional constraints are needed, as shown on the left. In our method, we use these adjugate variables as a parameterization for the rotation matrix. Now we can begin introducing our method in detail. Here's the overview. We start by incorporating 3D and 2D data through an orthographic projection for initialization, and then iteratively refine the solution using the LHM pipeline. Our method begins by solving the orthographic projection error analytically. Here, P, parameterized by the adjugate variables Qij, represents the first 2 rows of the rotation matrix. Since depth is arbitrary in orthographic projection, we can ignore the 3rd row. Ti2 are the first 2 components of the translation vector. P and U denote the 3D scene points and their homogeneous projections. Expanding this objective naturally produces cross terms in X, Y, Z, U, V. For convenience, we collect these terms into a data matrix. Now we move to the core of our method, DRaM, a closed-form solution for initializing the rotation. As mentioned earlier, we parameterize the first 2 rows of the rotation matrix and substitute it into the orthographic projection arrow. This leads to a polynomial in the adjugate variables up to 2nd order, with coefficients given by cross terms of x, y, z, u, v. To obtain the optimal p, we take derivatives with respect to all adjugate variables, enforcing only the unit Quaternion constraint. For further details, we invite the audience to refer to our paper or to Andrew Hansen's original derivation. This gives us the first 2 rows of the optimal rotation. The 3rd row is obtained as their cross product, and together they form our estimated rotation, R tilde. Each entry of this matrix is expressed as a determinant ratio of a submatrix of the data matrix we introduced on the previous slide, which is shown again here at the top right corner. We refine our estimated rotation using the Hager Mjolsness iterative scheme, which minimizes the collinearity error. This error measures the discrepancy between 3D scene points and their corresponding rays emitted from image pixels, resolved through a Gram-Schmidt-like process. Here, Vk denotes the unit ray vector associated with the pixel observation Uk. Since this error is not solvable analytically, the LHM scheme alternates between fixing R and solving for the optimal T, iterating until convergence. Unlike our initialization, which comes from an exact orthographic projection, the original LHM initializes R by registering the 3D cloud to its weak perspective approximation. In the next slide, we will show that our solution provides a significantly better initialization. Here are our key results. The figure on the left shows that our initialization is significantly better than LHM's weak perspective approximation, where they rely on a least Quaternion solution for point registration. The middle figure highlights the efficiency of our method. Both the number of points and the number of iterations can be tuned flexibly without sacrificing accuracy, remaining comparable to state-of-the-art methods like SQPNP. The tables on the right demonstrate that our method also performs strongly on real-world datasets, including TUM-RGBD and EuRoC MAV. At the last part, it is worth mentioning a key limitation of DRaM. Because it relies on a closed-form solution for orthographic projection, the method becomes less effective in planar scenarios. These cases introduce strong geometric ambiguity. The determinant of the self-covariance matrix vanishes, which can lead to inaccurate estimates. In our experiments, perturbing a plane with different noise levels shows a quasi-planar crossover, where DRaM begins to outperform weak perspective. In practice, we treat weak perspective as a fallback when the points are not well distributed.